Welcome to this explainer on the foundational language of precision engineering. Today, we are solving the ultimate manufacturing mystery. Why do parts pass inspection on paper but completely fail on the assembly floor? By the end of this, you'll know exactly why engineers who actually understand this language get parts right the first time, and why the ones who don't are just doomed to keep reordering expensive scrap.
Picture this scenario. A beautiful, incredibly expensive machined part just arrived on your desk. Quality control measured it, and every single dimension falls perfectly within its plus or minus tolerances. It passed. Everyone signed off on it. But then, you take it down to the assembly floor, you try to slide a bolt through it, and it just doesn't fit. The part is useless. So, what exactly went wrong?
Well, take a look at this stark comparison. On the left side, you've got traditional coordinate tolerancing, just your standard ambiguous plus and minus limits. Now look at the right. That is the exact same part, but it's defined with GD&T, using geometric precision constraints. I want you to ask yourself right now, which one of these actually guarantees the part is going to work? The one on the left leaves massive room for interpretation. The one on the right, it leaves absolutely nothing to chance. And look, we're not just nerding out over abstract geometry here. We're talking about real bottom-line dollars. That ambiguity you get from traditional tolerancing, it's a $10,000 mistake just waiting to happen. Relying solely on plus-minus limits is a huge financial drain. It causes ballooning scrap rates, endless cycles of rework, and incredibly bloated inspection times, while your team tries to figure out why a quote-unquote good part won't actually fit together. Enter the solution. The ASME Y14.5 standard. This is the engineering product definition standard. Think of it as the ultimate internationally recognized rulebook. It's the definitive guide that takes all that manufacturing ambiguity and replaces it with absolute mathematical certainty. To truly master this rulebook, we have to start by nailing down one fundamental distinction. What is the difference between a dimension and a feature? A dimension is literally just a number. It's stating that a clearance hole must be exactly 6.44 millimeters in diameter. A feature, on the other hand, is the actual, tangible, physical geometry itself. To make this super concrete, we're going to follow a simple metal bracket with a clearance hole as our running example for this entire masterclass. Let's watch how that old ambiguity guarantees real-world failure for our bracket. Step 1. The engineer designs the bracket with a standard plus-minus tolerance for the hole size. Step 2. The machinist makes the part, cutting it right to the absolute edge of that tolerance limit. The caliper says it's technically the right size. But step 3, out in the real world, the actual axis of that hole varies obliquely. It's tilting completely out of perpendicularity with the surface. So by step 4, when you drop the fastener in, it fails to clear. The dimension was right, but the physical feature failed. This is exactly where GD&T flexes its mathematical muscles. Straight from Appendix B of the standard, we have the floating fastener case. The formula is beautifully simple. H equals F plus T. That means the clearance hole minimum size must equal the fastener maximum diameter plus the positional tolerance. By defining the tolerance of the actual geometry's position, not just the size of the hole, GD&T mathematically guarantees that bolt will fit into that bracket every single time. So we know it works, but here is the exact part where most engineers get it completely wrong. Time for a quick pop quiz. If we're applying a position tolerance to our bracket's hole to make sure the bolt actually drops in, which of the major geometric categories does that position symbol belong to? Think about what it's physically controlling on the part. Well, if you guessed location, you absolutely nailed it. The crucial point here is that position falls squarely under the location category. It controls exactly where a feature is located in space relative to your datums, not just how big or small the drill bit was. This is the exact constraint that prevents that dreaded oblique drift we saw ruin our bracket earlier. This framework right here is your ultimate roadmap for the rest of this series. The standard outlines 14 primary symbols, and they are grouped into 5 strict categories. You've got form, which controls the shape of a single feature, orientation for managing angles relative to a datum, location, which we just tackled, profile for dictating the outline of complex surfaces, and runout, dealing with variation during rotation. Keep this mental map handy because we're going to be referencing it heavily, especially when we get into the truth about runout in Lesson 4. Now, once you've got these fundamentals down, it gets really exciting. Take a look at these advanced applications straight from the standard, composite positional tolerancing. This literally allows you to control massive patterns of features, like a huge grid of bolt holes, by constraining both the pattern locating zone and the feature relating zone all at the exact same time. It might look like a lot of heavy math right now, but I promise you, it's just the natural evolution of the core language we're learning today. So let's stop guessing, all right? Stop just hoping parts will miraculously assemble. It's time to start speaking the language of precision. Engineers and inspectors who understand this geometric framework completely eliminate ambiguity. They crush their scrap rates, and they design parts that work exactly as intended, straight off the machine. Think about it. If one ambiguous tolerance callout can cost you 10 grand in scrap, what is your current blueprint language actually costing your operation right now? You know why GD&T is critical, but can you actually read it in the wild? In Lesson 2, we're going to crack open the exact compartments of a feature control frame. By the end of it, you'll be able to instantly decode the tolerance zone, the shape modifier, and the datum references of any blueprint like an absolute pro. See you there.
Let's just jump right into it. If you've ever stared down an engineering blueprint and felt completely overwhelmed by that alphabet soup of symbols, well, you are definitely in the right place today. We're decoding the feature control frame using the exact rules set by the ASME Y14.5 standard.
This tiny little rectangular box just told a machinist exactly how to manufacture a part, and it told a quality inspector exactly how to check it. Seriously, it's the ultimate source of truth. If you can't read it, you literally can't make the part right. But stick with me, because by the end of this explainer, you're going to be able to decode any of these on site.
Okay, freeze right here for a second. Take a look at the sheer amount of data packed into this dense, multi-datum feature control frame. Go ahead and try to guess what all these geometric symbols, modifiers, and letters actually mean before we break it all down together. Like, what's that circle with the crosshair? And what on earth does that circled M do? So the secret to mastering this whole thing is actually incredibly simple. You just read it exactly like you'd read a sentence, from left to right. Every single feature control frame is broken up into compartments that follow a really strict logical order. You start on the far left with the geometric symbol, you move into the middle for the tolerance value and its modifiers, and you finish up on the right side with the datum references. Let's walk through this sentence piece by piece.
Step 1. First up on the far left, we have the geometric characteristic symbol. This dictates exactly what type of control we're applying to the feature. It could be a control for form, like flatness or straightness, or maybe profile. But in our running example here with that crosshair symbol, that's a location control for position. It tells us precisely what we're controlling right out of the date.
Moving on to step 2, let's see how this builds. This middle section holds the tolerance value, giving us the actual numerical size of our acceptable zone. Here we've got a 0.25, meaning our tolerance zone is 0.25 units wide, and the manufactured feature has to live perfectly inside that specific boundary to pass inspection. But a number all by itself isn't quite enough, is it? We need to know the shape of that boundary.
And that brings us to a massive trap. The diameter symbol, that little circle with a slash through it. Missing this is a huge mistake that causes real headaches on the shop floor. If that symbol is sitting right before your tolerance number, your tolerance zone is a three-dimensional cylindrical space. But if it's missing, you're stuck with two parallel planes. It's literally like trying to fit a round peg into a square hole if you get this wrong.
Now, the real game changer in this middle section is the material condition modifier, specifically the circled M, which stands for maximum material condition, or MMC. When you see this, it means your tolerance zone isn't just static. It dynamically allows for extra geometric tolerance as the feature's actual size departs from its maximum material limit. Put simply, this is where machinists can actually earn bonus tolerance. It makes manufacturing easier, it makes it cheaper, and it still guarantees the parts will actually fit together.
Just to show you how wild this is, compare a standard frame to one with an MMC modifier. They look almost identical on paper, right? But adding just that one tiny M modifier completely changes the physical reality of the part. The rigid frame means you get exactly 0.25 millimeters of position tolerance no matter what. But the frame with the MMC modifier, that gives the machinist flexibility. It fundamentally changes how you fixture and inspect the part. It's one of those rare times an engineer actually makes a machinist's life easier.
All right, step 3. Finally, we read the right side of our sentence, the datum references. You can have primary, secondary, and tertiary datums. Think of these letters as anchors. They lock our 0.25 cylindrical tolerance zone into a physical datum reference frame, a strict coordinate system established by actual physical features on the part. Without them, our tolerance zone is just kind of floating aimlessly in space.
Okay, before we go any further, I need you to pay super close attention to this next point. The order in which those datum letters appear is about to completely change everything you think this callout means. Datum precedence is read strictly left to right. It is not alphabetical. The very first letter you see is the primary datum. It establishes the first plane of contact and constrains a minimum of 3 degrees of freedom, requiring at least 3 points of contact on the inspection tooling. The secondary datum, right next to it, only constrains 2 degrees of freedom with 2 points of contact. And the tertiary datum on the right finishes it all up by constraining that last remaining degree of freedom with just a single point of contact.
So, why does that order matter so much? Well, if we have the exact same part, but we just swapped the primary and secondary datums in the callout, changing ABC to BAC, we've basically created a totally different set of instructions. The part is now physically fixtured against datum B first instead of A, which means a part that passes inspection under the first frame might completely fail under the second one, just because of how it rests on the table.
Let's quickly review the most expensive misreads people make when dealing with these frames. First, assuming datums are alphabetical instead of strictly reading them in left-to-right order of precedence. Second, missing that crucial diameter symbol and accidentally inspecting a cylinder as a flat plane. And third, ignoring material condition modifiers like MMC, which literally just throws away perfectly good bonus tolerance and scraps parts that are actually totally fine. Okay, quiz time. Let's put these new decoding skills to the test. Think back to our set and structure. If I show you a position control frame and a flatness control frame side by side, which one of these absolutely requires datum references at the end of the sentence? Take a second and lock in your answer. All right, if you guessed position, you absolutely nailed it. As the standard rules outline, orientation, location, and runout tolerances, like position, always have to relate back to a datum. They tell you where a feature is compared to the rest of the part. But form tolerances, like flatness, they never require a datum. They literally only control a feature relative to itself.
Which perfectly sets up our next explainer. In Lesson 3, we're diving deep into form tolerances. We'll explore exactly why they're the only geometric controls that totally rebel against the rules we just learned, operating completely on their own without ever needing a datum reference frame. I mean, how do you even measure a surface without referencing another surface? Join us next time to find out. Keep practicing reading those frames left to right, and I'll catch you in the next lesson.
Imagine you're holding a freshly machined solid metal block. You take your precision calipers, you measure the height, you check the width, you check the length, everything is dead on. It's perfectly within the specified plus or minus size tolerances on the blueprint. So you confidently send it down to the assembly line, but when they try to actually mate it with another component, it completely fails to fit. Or, maybe it's a cylindrical pipe that measures perfectly, but when you install it, it utterly fails to seal and just leaks fluid everywhere. How is that even possible? How can a part measure perfectly, yet fail completely? Well, welcome to Lesson 3 of our GD&T Explainer Masterclass, where we're going to solve that exact mystery. To really understand this manufacturing mystery, let's look at a comparison. On one side, we have a perfectly flat, pristine, rectangular block. On the other side, we have an exaggeratedly warped, wavy, almost potato-shaped block. But here is the massive pattern interrupt. Both of these blocks can technically pass the exact same plus and minus size limits. No way, right? But it's true. And that's because basic size limits just check the local distance between two opposing points. You can take a micrometer to the valleys and peaks of that wavy block, and as long as that local distance is within tolerance, it technically passes size inspection. So size limits alone absolutely do not perfectly control a part's overall shape. So, I gotta ask you, which one of these actually works in a real-world assembly? Obviously the flat one, for sure. But if a basic set of calipers or micrometers can't tell the difference between a perfectly flat surface and a wavy potato, how do we catch that defective part before it ruins an entire engine block or a critical aerospace build? Well, to catch that wavy part, we need a highly specialized set of rules. We need form tolerances. Okay, let's dive into this. Looking directly at the ASME Y14.5 standard for the 14 geometric characteristic symbols, I want to draw your attention right to the top category, form. You've got straightness, flatness, circularity, and cylindricity. But the single most important rule of this entire category is sitting right there in the far right column. Look at the datum reference required section. It says no all the way down. Form tolerances never use datums. So, what does no datums actually mean in everyday engineering practice? It means that these four symbols are entirely self-referencing. As the ASME standard defines it, we're controlling a geometric feature strictly relative to itself, completely independent of any other feature or datum reference frame. We aren't orienting it to the bottom of the part, we aren't locating it from a hole, we're not squaring it to a sidewall, nothing like that. And, this dramatically simplifies things for us. We're purely evaluating the independent shape of this one specific feature. Is it straight? Is it flat? Is it round? That is literally all we care about right now.
Before we look at the individual symbols, let's set up a quick mental model. We can map all four of our form symbols across a super simple 2D to 3D logic board. For the columns, we have the type of geometry, straight and flat features versus rounded features. And for the rows, we have dimensionality. Are we looking at a 2D cross-section or are we looking at a full 3D surface? If you can remember this grid, it's like a giant puzzle. You can pattern match the logic of the entire form category. Let's start up in the top left.
Number 1. Straightness, 2D line elements. Because straightness is a 2D symbol, we're focusing on evaluating a surface just one single line at a time. The standard dictates that straightness limits the variation of line elements in a single direction. The visual you really need to lock into your brain here is the tolerance zone itself. For straightness, this zone is always bounded by two perfectly parallel lines. Just imagine resting a precision straight edge right on the surface of your part. You're simply verifying that the single line profile of that surface doesn't dip, bow, or wave outside of the tiny gap between those two parallel lines. Oh, and as a really important side note, the standard also specifies that if you attach the straightness symbol to a size dimension of a cylinder, it can uniquely apply to what's called a derived median line, which is essentially the abstract imperfect centerline of the feature. But for basic surface straightness, just remember, one line bounded by two parallel lines. Number 2. Flatness 3D surface control. Let's move to and see how this builds from the top left of our matrix down to the bottom left. We're upgrading from evaluating a 2D line to an entire 3D surface. Flatness simply takes that 2D straightness concept and sweeps it across a full area. The standard tells us that flatness requires all points of a surface to lie within a tolerance zone bounded by two parallel planes. So, instead of two parallel lines, imagine trapping your entire part's surface between two perfectly flat parallel sheets of glass. If any point on that entire surface bows up or warps down enough to break through the glass, the part is scrapped. The standard even notes that flatness can be applied on a unit basis. That means you can specify that a surface must remain extremely flat within a small specific area, say like a 25 by 25 millimeter square, which limits those abrupt surface variations across a much larger plate. Number 3. Circularity 2D cross-sections. Now, let's switch gears from flat geometry over to round parts, moving to the top right of our mental matrix. The rule for circularity, which is sometimes called roundness, is that each cross-section of a surface must independently lie between two concentric circles. Now, what's really interesting about this is that word, independently. Because we're in the 2D row of our matrix, we're evaluating the cylinder slice by slice, literally just like a loaf of bread. The standard dictates that this applies independently at any plane. That means each individual slice can actually have a slightly different center point, as long as the surface of that specific slice is perfectly sandwiched between its own two concentric circles. So it definitely catches if a slice is oval-shaped or egg-shaped, but it doesn't care at all how those slices stack up against each other. So time for a quick quiz to test your new GD&T X-ray vision. Imagine a cylindrical pin. You check the circularity of 50 different slices, and every single slice perfectly passes 2D circularity. It's round at every single cross-section. But when you look at the pin from the side, it bulges in the middle like a barrel, or maybe it pinches in the middle, becoming what we call wasted. The standard specifically warns that full straightness might not be available in cases of wasting or barreling. So if circularity only checks independent 2D slices, what symbol actually catches a part that is wavy end to end? Number 4, cylindricity, 3D round geometry. To catch that barreled or wasted defect, we have to move to the bottom right of our matrix and unleash the absolute boss-level 3D symbol for round geometry. Cylindricity is the one symbol that practically everyone underestimates, but manufacturers respect it deeply because it's a strict, all-encompassing control. As the ASME standard explicitly points out, cylindricity is a massive composite control of form that commands three things all at once: the straightness of the cylinder, the circularity of the cylinder, and the taper of the cylinder. It evaluates the entire feature at the exact same time. And this brilliantly illustrates the difference between 2D and 3D geometric controls. Because it's a 3D tolerance, cylindricity creates one single tolerance zone bounded by two perfectly concentric cylinders for the entire surface simultaneously. Unlike our circularity slices where the center points could kind of drift around, cylindricity forces the entire length of the surface into one rigid 3D jacket. It locks both the circular elements and the longitudinal elements together. If your part is barreled, wasted, or tapered, even if it's perfectly round at every individual slice, it will absolutely crash through those two concentric 3D boundary cylinders and fail inspection.
So look at how beautifully simple this system is when you really break it down. We have two 2D controls, straightness and circularity, and we have two 3D controls, flatness and cylindricity. We use parallel boundaries for flat things and concentric boundaries for round things. And the core takeaway that ties all of this together is this direct quote from our reference documents. Form tolerances never reference a datum, they control a feature relative to itself. We have officially mastered how to evaluate independent features without needing a single external reference point. But I want to leave you with a bit of a provocative thought here. Let's say you've manufactured a pin with absolutely perfect cylindricity and a block with absolutely perfect flatness. That's great, but how do you ensure that perfectly cylindrical pin is located in the exact right spot on that perfectly flat block, right? How do we relate these perfect shapes to each other to build a machine that actually functions? Well, that requires exactly what we completely ignored today. So the crucial point is we need datums. Orientation, location, and runout tolerances all absolutely require a datum reference frame, and that is exactly what we are going to build from the ground up in Lesson 4. I'll see you there.
All right, let's jump right into Lesson 4, Datums and the Datum Reference Frame. Today we're tackling a pretty wild paradox that sits right at the heart of engineering and manufacturing.
You see, every single dimensional inspection, literally every quality check you run on a part, requires a theoretical, absolutely perfect plane to measure from. But here's the catch. That perfect plane? It doesn't actually exist anywhere on a real manufactured part. Not on the smoothest milled surface, not on the most precisely turned cylinder. So let me ask you this. If that perfect theoretical plane doesn't exist, what is a machinist actually touching when they set up their indicators to measure from, say, datum A? If you zoom in with a microscope, that flat line you see on a blueprint is actually a jagged mountain range of microscopic peaks and valleys. So we've got to solve this core mystery. What exactly are we measuring against out there in the real world?
Okay, let's look at a classic setup. We've got the part's actual physical surface on one side and a heavy, precision-ground granite surface plate that the part is sitting on the other. I want you to guess for a second, which one of these is the actual datum? Is it the part itself, or is it that granite plate underneath it? Take a guess. Well, if you guess the part, you're wrong. And if you guess the granite plate, you're actually also wrong. Believe it or not, this is the exact concept that most engineers and honestly, even seasoned machinists get wrong.
To understand why, we have to look at the strict definitions from the ASME Y14.5 standard. A datum is defined as a theoretically exact point axis or plane. It's derived from what the standard calls a true geometric counterpart. The absolutely crucial takeaway here is that the datum is perfect by definition. Zero variation, zero surface roughness, zero form error. Because it's so perfect, it's basically a ghost. It only exists in theory, in the math, and in your CAD model. It literally does not exist on your physical part.
Now, what you're actually holding in your hand, or what the machinist has clamped in the vise, is the datum feature. The datum feature is the actual physical feature on the part itself, like a face, a hole, or a slot, that's identified by that little datum symbol on the drawing. And unlike our perfect theoretical ghost datum, the datum feature is highly imperfect. It's bumpy, it might be slightly warped, maybe a bit tapered, but it's the real-world surface that we have to use to try and establish our perfect datum. So how do we bring that ghost into the physical world? Well, this is the answer to our trick question from earlier. That granite surface plate, or a precision gauge pin, or a machine chuck, those are datum feature simulators. They're the physical tooling elements that contact your bumpy datum feature to simulate the perfect theoretical datum. They act as the physical embodiment of that true geometric counterpart. Now, they aren't perfectly flawless, obviously, but they're of such incredibly high quality that the planes or axis derived from them act as our datums during manufacturing and inspection.
So, here's the real kicker. Just because you slap a datum label on a drawing feature does not magically make it flat or perfectly round. Because datum features are real, physical, and imperfect. The ASME standard explicitly states they must be controlled themselves. Think about it. If you're going to anchor your entire measurement system to a surface, that surface needs a control, like a flatness tolerance or a tightly controlled size dimension so that it actually sits on the Datum feature simulator reliably without just rocking wildly back and forth.
And that brings us to how we actually lock a part down for measurement, using what's known as the 3-2-1 point contact rule. To fully stabilize an object, we specify datums in a very strict order of precedence. Step 1 is the primary datum, which requires a minimum of 3 points of contact, kind of like a three-legged stool, which, as you know, never wobbles. Step 2 is the secondary datum, requiring a minimum of 2 points of contact. And finally, step 3 is the tertiary datum, requiring just 1 minimum point of contact. This exact step-by-step sequence is how we build our datum reference frame.
So let's test your intuition on how this physical constraint actually works in practice. Quick quiz. Imagine you take a part and you just simply rest its bottom face onto a flat granite surface plate. So you've applied a primary planar datum. How many degrees of freedom do you think remain? Like, how many ways can that part still move? Think about it for a second before we start our countdown.
Okay, to answer that, we actually have to start at the maximum. Before any datums are applied, a rigid body floating freely in 3D space starts with exactly 6 degrees of freedom. 6 independent ways it can potentially move around.
Let's break this down really quick. Those 6 movements are basically 3 translations and 3 rotations. The part can translate, which just means slide, back and forth along the x-axis, the y-axis, or the z-axis. And it can also rotate or tilt around the x-axis, around the y-axis, and around the z-axis. Picture a spaceship floating totally untethered in outer space. To inspect a part accurately, we have to lock down all 6 of these movements relative to our measurement equipment.
So, jumping back to our quiz. When you place that part down onto the primary planar datum, the surface plate, making contact at those 3 minimum high points, you instantly lock down 3 degrees of freedom. The part can no longer translate down through the solid plate, right? And it can no longer tilt or rotate in the 2 directions against that flat plate. That leaves us with 3 degrees of freedom remaining. The part can still slide around flat on the plate in X and Y, and it can still spin around like a top.
Next, we push the part up against a second block, our secondary datum simulator, which has to be perfectly perpendicular to the primary. This makes contact at a minimum of 2 points. By doing this, we stop it from sliding in one of those directions, and we stop it from spinning. Boom! We've just locked down 2 more degrees of freedom. We are now left with just 1 single degree of freedom. The part can only slide back and forth along that secondary block.
Finally, we slide the part until it bumps against a third block, the tertiary datum feature simulator. This makes that final 1 minimum point of contact. It stops the part from sliding in that last remaining direction. And there it is. We've removed the final degree of freedom. The counter hits 0, the part is perfectly and immovably secured in the datum reference frame, and our X, Y, and Z coordinate system is completely locked in for inspection.
Now this brings up a massive, absolutely crucial wake-up call for anyone designing or inspecting parts. Datum order isn't just some paperwork formality. If you have a feature control frame that says datums A, B, and C, and you decide to just casually swap it to B, A, C on the machine, you haven't just rearranged letters. You have fundamentally shifted how those degrees of freedom are constrained. You're changing which surface gets 3 points of contact versus 2 points. And because real parts aren't perfectly square, swapping datums literally tilts the part differently in the inspection fixture. That means your entire tolerance zone moves in physical space. No way around it.
And this brilliantly illustrates the rules right out of our reference document. If you look at the feature control frame structure, you'll see the 4th compartment lists the datums. The order they're read, strictly left to right, is known as datum precedence. It's an absolute rigid set of instructions for the inspector on exactly the sequence to strip away those 6 degrees of freedom. Primary first, secondary next, tertiary last. It dictates exactly how the part meets the gauge.
So now that we've successfully built our 6 degree of freedom anchor, the datum reference frame, the obvious question is, how do we actually start applying geometric tolerances relative to it? Well, we're going to tackle exactly that in Lesson 5 of this explainer, where we dive into orientation tolerances, things like perpendicularity, angularity, and parallelism. These are the very first symbols that absolutely require this exact framework to function. But hey, before you jump to that next lesson, ask yourself this. Look at the blueprints on your desk right now. Do those datum features actually have tolerances controlling their own form? Or are you just assuming they're perfect ghosts? Definitely something to think about. I'll catch you in the next one. All right, picture this. You're out on the shop floor and you've just finished machining this absolutely critical shaft. You pull out your instruments, check the diameter, and hey, it's perfectly within its limits of size. You check it for straightness, and the form is literally flawless. But then you hand it over for assembly, and it just jams. It flat out won't fit into the mating part. It's a complete failure. So what happened? Well, because that perfectly round, perfectly straight shaft happens to be tilted just slightly relative to its mounting face. It's a hugely frustrating shop floor nightmare, but it proves one fundamental rule in engineering. Having perfect form simply isn't enough. So today, in this explainer, we're going to fix that. By the end of our time together, you will have completely mastered the 3 specific GD&T symbols that control exactly how a feature is angled relative to a datum. We're going to make sure your perfect parts actually assemble perfectly every single time.
Okay, quick pattern interrupt here. Think about 3 identical shafts mounted on a flat base. One is standing straight up at a perfect 90-degree angle. Another is laying completely flat at 0 degrees. And the middle one? It's leaning over at this bizarre 47-degree angle. Now, if you run a basic straightness check on all 3 of these shafts, every single one of them is going to pass with flying colors. So ask yourself, which one is actually correct? Well, the trick answer is that you have absolutely no idea. Not until you look at the blueprint's orientation tolerances anyway. So let's dive into the rules and see how this builds the entire foundation of our explainer today.
To solve the mystery of the tilted shaft, the ASME Y14.5 standard actually gives us exactly 3 tools. We call these the orientation symbols. Now, unlike form tolerances, things like straightness or flatness that just look at a feature all by itself in isolation, orientation tolerances exist specifically to control a relationship. They tell the manufacturer exactly how a feature is angled relative to a datum.
Let's kick things off with our first core beat, perpendicularity. According to the ASME standard, perpendicularity is defined as the condition of a surface, center plane, or axis at exactly 90 degrees to a datum. Basically, what this does is rigidly lock your feature into a right-angle relationship with its reference point. So, if you've got a flat base and you need a pin standing straight up out of it without leaning to the left or the right, you are absolutely going to use perpendicularity. And honestly, the magic here is in the sheer simplicity of this number, 90. Whenever you're looking at an engineering drawing and you spot that upside-down T symbol for perpendicularity, I want your brain to instantly flash this exact number, 90 degrees. That is literally the one and only angle that perpendicularity cares about. It is the undisputed, absolute ruler of the right angle.
But what if your design actually requires a part to be purposely tilted? Well, that brings us to our second symbol, angularity. In the GD&T framework, angularity is the condition of a feature at any specified basic angle, other than 0 or 90 degrees, from a datum. You can really think of angularity as the ultimate versatile catch-all. If your angle isn't perfectly flat and it isn't perfectly straight up, angularity is the symbol stepping in to do all the heavy lifting.
The really crucial point to remember is this. If the blueprint calls for a 47-degree tilt or a 15-degree taper or a 72-degree angle, angularity is the required symbol. And notice that we call it a basic angle. In GD&T, a basic dimension is a theoretically exact value. You'll usually see it enclosed in a little rectangular box right there on the drawing. The angularity tolerance zone is then built perfectly and evenly around that theoretically perfect 47-degree basic angle.
Finally, we have the third symbol in our orientation trifecta, and that is parallelism. The standard defines this as the condition of a line element, surface, center plane, or axis at a basic 0 degree or parallel angle relative to one or more datum planes or axis. In plain English, it dictates that your feature has to remain completely equidistant from its reference base across its entire length.
And just like perpendicularity completely owned the number 90, parallelism completely owns 0. You definitely want to lock this concept in. Parallelism is exclusively the champion of the 0-degree orientation. If you want 2 surfaces to act like perfectly level train tracks that literally never converge and never diverge, use parallelism to lock them in at 0 degrees.
Thinking about these 3 together brilliantly illustrates how they interact. Imagine taking a single shaft feature and swapping these callouts sequentially. First, you apply perpendicularity, and boom, the tolerance zone snaps the allowable tilt to perfectly straight up and down at 90 degrees. Then, you swap the symbol out for angularity with a basic angle of 47 degrees. Instantly, the tolerance zone tilts over, allowing the shaft to lean precisely to that angle. Finally, you apply parallelism, and the tolerance zone slams completely shut to 0 degrees, forcing the shaft to lay flat against the reference plane. It's the exact same physical feature, controlled in 3 completely different ways based solely on which symbol you chose.
But here's the catch. None of this works without the golden rule. I actually want to read this exact quote directly from the ASME Y14.5 standard, where it defines orientation. It says, these conditions must exist, quote, relative to one or more datum planes or datum axes, end quote. This is the absolute, non-negotiable rule of orientation tolerances. You cannot, under any circumstances, use perpendicularity, angularity, or parallelism on a feature control frame without referencing at least one datum. It just doesn't work.
And this is a direct callback to our earlier explainer where we covered the datum reference frame. Remember, a datum is a theoretically exact plane, axis, or point. It is your anchor. I mean, think about it logically for a second. You can't just point at a pole and say it's perpendicular without answering the obvious follow-up question. Perpendicular to what? You absolutely cannot control an angle without a fixed base to measure from. The datum is that base.
Okay, I need your full attention for this next part, because this is a massive mid-lesson trap where so many people get completely tangled up. We've talked all about the angles themselves. But what about the invisible box that's actually controlling the error? Let's talk about section 9.3.2 of the standard, tolerance zone shapes. There is one huge mistake people make all the time. They just assume that perpendicularity or angularity always produce this flat, sandwich-like tolerance zone. But actually, depending on what kind of feature you're controlling, the true 3D shape of your tolerance zone can be completely different.
The standard specifically outlines 3 very distinct tolerance zones for orientation. Step 1 is a tolerance zone defined by 2 parallel planes. Step 2 is a cylindrical tolerance zone, and Step 3 is a tolerance zone defined by 2 parallel lines for individual line elements. Why does this matter? Well, because if you're the machinist making the part, or the quality inspector measuring it, you absolutely have to know what physical space your feature is actually allowed to live inside.
So let's break down the absolutely crucial difference between those first 2 shapes. You have to ask, are you controlling a flat surface or are you controlling an axis? If you apply perpendicularity to a flat block of metal, your tolerance zone is 2 parallel planes. You're essentially trapping that flat surface between 2 perfectly flat, invisible panes of glass separated by whatever your tolerance value is. But if you apply perpendicularity to a drilled hole or a cylindrical pin, and you use the diameter modifier in your feature control frame, you're no longer trapping a flat surface. You are controlling the feature's axis, trapping it inside a 3D tube-shaped cylindrical zone. And trapping a plane between 2 sheets of glass is fundamentally different than trapping an axis inside a virtual pipe.
All right, let's shift the pacing a bit here. You have just absorbed a ton of high-level GD&T theory straight out of the ASME standard. Now, I want to turn you into an active participant. We're going to do a rapid-fire quiz to really lock in everything you've just learned about orientation. You ready for this?
I'm throwing 3 basic angle values your way, and I challenge you to mentally lock in your answers right now. Match these angles to their correct GD&T symbol. First up, 0 degrees. Second, 90 degrees. And third, a custom 47 degrees. Think back to those magic numbers we talked about. You got your answers? Okay, let's do the reveal. If you guessed that 0 degrees is parallelism, you are absolutely correct. 90 degrees goes strictly to perpendicularity. And that wild 47-degree callout, yep, that belongs to our versatile catch-all, angularity. If you nail those, congratulations. You've just taken a massive step toward GD&T mastery by truly understanding how orientation controls actually function on a blueprint.
But as always, our journey doesn't quite end here. Think about the logical flow of manufacturing a part. First, a part needs basic form. It needs to be round or straight. Next, as we learned today, it needs proper orientation. It needs to be perfectly tilted, parallel, or perpendicular to its datum anchor. But once a feature has its form and its orientation locked in, what's missing? It needs an exact pinpoint location in 3-dimensional space.
And that brings us to the ultimate cliffhanger. In our next explainer, we are going to tackle the true final boss of geometric dimensioning and tolerancing, location tolerances. Specifically, we'll be diving incredibly deep into the position symbol. You now know exactly how to angle your features perfectly, but what happens when a perfectly angled feature is drilled a full inch off-center? Well, join me next time to find out. See you then! YouTube metadata package. Video title, Why Perfect Parts Fail, GD&T Orientation Tolerances. Thumbnail concepts. 1. A brightly colored 3D shaft tilted awkwardly inside a hole with the big red X drawn over it. Large, bold text overlay. Perfect but fails. 2.
3 identical 3D shafts shown side by side at slight angles, 0 degrees, 90 degrees, 47 degrees, on a flat datum plane. Text overlay pointing to all 3. Which one is right? 3. A glowing blue GD&T feature control frame hovering over a mechanical part, with a bright yellow arrow pointing aggressively to the datum section. Text overlay, the one missing rule.
Welcome back, everyone, to Lesson 6 of our GD&T Explainer. Today, we're tackling a topic that is honestly the absolute backbone of modern manufacturing and assembly, and that is location tolerances. So let's just jump right in, because by the end of this explainer, we're going to completely demystify how these specific tolerances work, how to read them fluently, and most importantly, how they prevent those catastrophic, insanely expensive manufacturing disasters right there on the assembly floor.
Okay, we've all seen this incredibly frustrating scenario. You've got a standard bolt pattern. Every single hole is measured. Every single hole technically passes its individual plus or minus X and Y coordinate inspection. But then you take that part to the assembly line and the mating components physically collide. The bolts just won't go through. No way, right? It's a total illusion. How in the world can parts be in tolerance according to the drawing, but completely fail to function in reality?
Well, the culprit here is legacy coordinate dimensioning. Think about it. When you use traditional plus-minus dimensioning to locate a hole, the center of your hole is forced to fall exactly inside a rigid, restrictive square tolerance box. But true position tolerancing flips the script by creating a dynamic circular boundary. Both methods might technically use the exact same numeric tolerance value, but the geometry of the zone, it completely changes the game.
Let's do a quick mental quiz. If you have a square tolerance zone and a circular tolerance zone driven by the exact same numeric value, let's say a 0.5 millimeter allowance, which one actually gives the machinist more usable area to work with? Take a second. Estimate in your head how much extra room that circle provides over the square. And hey, why does that even matter? Well, because more area means fewer rejected parts, which directly translates to massive, massive cost savings. Here's the huge secret. The answer is 57%. Yep. Position tolerancing mathematically gives you roughly 57% more usable manufacturing area compared to traditional coordinate dimensioning. A square zone arbitrarily chops off the corners of the allowable tolerances, but by using a circular position zone, we reclaim that diagonal distance as entirely usable, highly functional space. The bolts are still going to fit, but you are instantly rescuing perfectly good functional parts from the scrap bin and drastically lowering your production costs.
So, let's get into understanding position tolerance.
The really crucial takeaway here is that position tolerancing isn't just a different way to draw a picture. It's literally a financial and functional superpower for engineers and machinists. Now that we clearly see the immense value, let's break down the fundamental mechanics of how it actually works according to the ASME Y14.5 standard. Starting with the strict definition, positional tolerancing defines a theoretical boundary, which is very often a cylindrical zone, that's located exactly at the true position. The axis, or the surface of the feature you're controlling, absolutely must not violate this boundary. Basically, think of it as creating a perfect, invisible protective tube around the theoretically exact center of where your hole or pin is actually supposed to be.
To make this work, there are 3 mandatory ingredients you're always going to find when dealing with position tolerances. First, you need basic dimensions. These are the theoretically exact untolerance numbers usually enclosed in a box on the drawing that locate that exact true position. Second, you need to define a tolerance zone shape, which is almost always cylindrical, denoted by the diameter symbol. And third, you absolutely need datum references to lock down your part and constrain its degrees of freedom.
All right, so how do these 3 elements actually come together on a blueprint? You're going to see a rectangular box called a feature control frame, or FCF, pointing right to your feature. If you want to master location tolerances, you have to know how to decode this box fluently. Let's walk through the exact readout sequence step by step. First up in the box, you have the geometric characteristic symbol. In our case, the crosshairs for position. The next block contains your tolerance value. And hey, if you see the diameter symbol, you know for sure it's a cylindrical zone, say 0.25 millimeters. The third part is absolutely crucial. It houses any material condition modifiers, like the M inside a circle for maximum material condition. Finally, you have your datum references in strict order of precedence: primary A, secondary B, and tertiary C. Read all together, it sounds just like this. Position tolerance, 0.25 millimeter diameter zone at maximum material condition relative to datums A, B, and C.
Now, let's talk about the magic of MMC bonus tolerance.
I really want to pause right here and draw your attention back to that little M in a circle we just talked about. This is where things get really exciting. Applying the maximum material condition modifier is exactly how you can save thousands, sometimes tens of thousands of dollars in totally unnecessary rework and scrap. This is the magic of bonus tolerance. But to understand the bonus, we first got to understand the modifier. The ASME standard defines maximum material condition, or MMC, as the condition in which a feature of size contains the maximum amount of material within its stated limits of size. So for an internal feature, like a hole, maximum material means the hole is at its absolutely smallest allowable diameter. For an external feature, like a pin, it means the pin is at its largest allowable diameter.
Now, look at how this math actually works out in reality. When you specify position at MMC, your stated tolerance, let's say it's 0.25 millimeters, only strictly applies when the hole is drilled at its very smallest size. But check this out. As the actual physical hole departs from MMC, meaning the machinist drills it slightly bigger but still within the size limits, your positional tolerance zone legally grows by that exact same amount. So if the hole is 0.05 millimeters larger than MMC, you get a 0.05 millimeter bonus added directly to your location tolerance.
And this perfectly captures how GD&T mirrors physical reality. We don't just make this stuff up. This is directly from the ASME Y14.5 2018 standard, which states, when the size of the unrelated actual mating envelope departs from MMC, the positional tolerance increases. Think about it functionally for a second. If you drill a hole slightly larger, there is physically more wiggle room for the bolt to pass through. Bonus tolerance mathematically captures that reality, legally accepting perfectly functional parts that rigid, old-school coordinate dimensioning would have blindly thrown straight in the trash.
Which brings us to a bit of a graveyard. RIP concentricity and symmetry.
All right, we need to pivot to some highly controversial news, especially for the veteran draftsmen and engineers tuning in. While position tolerance has been solidifying its status as the absolute king of location controls, the 2018 ASME standard update brought a sudden, ruthless death to two legacy location symbols. Let's look back at them. Concentricity, which is those two target circles, and symmetry, which looks kind of like a three-line hamburger. Under older standards, concentricity required that the derived median points of all diametrically opposed elements share an axis with a datum axis. Symmetry similarly required that median points of opposed elements share a datum center plane. Both of these controls strictly relied on calculating theoretically derived median points, and both, of course, required datum references.
For decades, these were the go-to symbols for keeping parts centered. But when we compare those older practices directly against the modern ASME Y14.5 2018 release, we see a massive shift. As of 2018, both concentricity and symmetry were completely wiped out. They are banned. They literally no longer exist in the active standard.
So why would the ASME committee kill off such famous symbols? Well, the standard gives us the exact justification. Both have been eliminated because other characteristics provide more direct control. It does eliminate the confusion that surrounds these symbols and their misapplication. The reality out there on the shop floor was that finding derived median points is incredibly difficult, not to mention expensive, to inspect. In 99% of modern applications, a simple position tolerance or a runout tolerance does the exact same functional job, but is vastly easier to manufacture and measure. So the crucial point here is that position tolerance has officially taken over the duties of concentricity and symmetry, making our drawings cleaner and our inspections far more cost-effective.
Looking ahead, the ultimate symbol.
Now, if older, highly specific symbols are being retired and consolidated, what else can we use to control highly complex, irregular features that aren't just simple holes or pins? That question brings us directly to the doorstep of our next topic. In Lesson 7, we are going to unpack the undisputed heavyweight champion of the GD&T world, profile tolerances.
I want to leave you with this provocative thought as we wrap up today's explainer. Position tolerance gives you a 57% larger tolerance zone and handles location beautifully. But what if one single symbol was so incredibly versatile that it could theoretically replace almost every other tolerance type, form, orientation, and location in the entire standard? That is the sheer power of profile, and that's exactly what we're going to uncover in Lesson 7. Thank you so much for joining me to master location tolerances, and I will see you in the next explainer.
Welcome back. This is Lesson 7 of our GD&T Masterclass, and today we're tackling profile tolerances for both lines and surfaces. Let's just jump right in. I want you to imagine trying to tolerance a really complex shape, like, say, an aerodynamic automotive body panel, or one of those sweeping turbine blades.
How do you even go about writing a basic plus and minus dimension for a free-form curve like that? I mean, where are you even measuring from? Which exact point on that crazy curve gets the plus or minus? The reality is, using traditional coordinate dimensions for something like this is, well, it's practically impossible. It's just way too ambiguous. You really can't just slap a basic bilateral tolerance on a sweeping curve and expect the manufacturer to know exactly what you want. We need something better. We need what is essentially the absolute Swiss Army knife of the ASME standard.
So instead of dealing with those messy coordinate dimensions, picture this. Imagine a kind of tolerance tube that wraps perfectly around the part's mathematically ideal shape. The standard calls this the true profile. And guys, that is the raw power of the profile tolerance. Just think about it. What else controls form, size, orientation, and location all at once with just one symbol? Nothing. This one geometric characteristic consolidates a total nightmare of requirements into one clean, elegant boundary that the physical part absolutely has to fit inside. Now, before we get too deep into the advanced applications, we really need to distinguish between the two heavy hitters here. First up, we've got profile of a line. You can think of this as taking a 2D cross-section of your part. The tolerance zone only applies to the line elements along that one specific slice. It's kind of like slicing a loaf of bread and inspecting the crust on just one single piece. On the flip side, profile of a surface wraps the entire part in a full three-dimensional tolerance zone. It applies perfectly normal, meaning perpendicular, to the true profile at every single point. So while profile of a line controls elements individually, one by one, profile of a surface demands that the entire 3D surface stays perfectly within that established boundary. It's the whole shebang. If we take a step back and look at all 14 geometric characteristic symbols, a pretty distinct pattern starts to emerge. Think about form tolerances, right? Things like flatness or straightness. They never actually reference a datum because they're only controlling a feature relative to itself. Then you have runout and location tolerances, which absolutely always require a datum reference frame. But profile is uniquely listed as optional. And honestly, this is exactly where its true flexibility comes in. The way it behaves completely changes depending on your specific design intent and whether or not you decide to include datums in that feature control frame. Actually, let's test this concept out with a quick quiz. Imagine we have the exact same curved part, and we apply a profile tolerance to it. What is a datum-free profile callout actually controlling, especially when you compare it to one that's fully loaded with primary, secondary, and tertiary datum references? Take a second to really think about the degrees of freedom here. If we don't reference a datum, where exactly is that tolerance zone floating in space? All right, here's the big aha moment. Without datums, your profile tolerance is controlling the form, and potentially the size only. Basically, the shape of the part has to be correct, but that tolerance zone, it can float freely around in space. It's not tied down. But the second you add datums to the feature control frame, you lock that tolerance tube into a specific datum reference frame. You completely constrain its translational and rotational degrees of freedom. So now, not only does the shape have to be perfect, but it has to be perfectly located and perfectly oriented relative to your specified datums. Boom. Now, if you're wondering why engineers absolutely love this tool, it's because it saves you from handing a machinist a ridiculously cluttered drawing that looks like a spider web of dimensions. Profile can literally replace flatness, angularity, and position, all on one single callout. When you use profile of a surface and tie it to a datum reference frame, you are simultaneously telling the shop exactly how flat the surface needs to be, what exact angle it has to set at, and exactly where it must be located. It takes this confusing, messy document and turns it into something streamlined and beautiful. It's a real game changer. So by default, a profile tolerance zone is split perfectly down the middle, meaning half of it is inside the true profile and half is outside. But you aren't locked into that. Enter the unequally disposed modifier. It's represented by a U inside a little circle. And this is so cool because it allows you to push the tolerance zone entirely inside or entirely outside the true profile. The number right after that U symbol, that just indicates how much of the tolerance is in the direction that allows additional material. So say you have a 0.3 tolerance and it says U0. Well, that is a unilateral tolerance where all variation must remove material. It gives you absolute custom control over your boundaries. We also use a few specific modifiers to define the physical extent of the tolerance zone around the part's geometry. For instance, what if you have a massive profile but you only want to control a small curve? You just use the between symbol. You literally place reference letters on the drawing, and the tolerance only applies to that specific segment between those 2 points.
Conversely, if you want to wrap the entire cross-section that you're looking at, you use the all-around symbol. That's the little circle on the leader line. And hey, if you want to cover the whole 3D part, there's even an all-over symbol for that.
Okay, time for a quick advanced preview. Let's look at composite profile. This is essentially a two-step framework. The top half, the PLTZF, governs a pretty generous tolerance for locating the whole pattern relative to your datums. Then the bottom half, the FRZTF, is a much tighter tolerance for the features themselves. Now, don't worry about memorizing those alphabet soup acronyms right now. Just remember that it's an incredibly precise way to say, hey, the pattern as a whole can shift around a bit, but the shapes themselves, they must be perfectly formed and oriented.
And that brings us to one of the newest and frankly coolest additions to the standard, the Dynamic Profile Modifier from the ASME Y14.5 2018 revision. Highlighted by a little triangle symbol inside the feature control frame, this thing solves a massive headache for engineers. Basically, it allows a tolerance zone to expand or contract. That means you can tightly control the exact form and orientation of a feature, totally independently of its size. So the feature can uniformly progress in size, getting slightly thicker or slightly thinner, but its underlying shape and orientation are locked into a strict, tight tolerance zone. If you have parts that require perfect form regardless of their final machine thickness, this is for sure the way to go.
So we've seen today that Profile is undeniably the ultimate, most flexible tool out there for controlling static shapes. I mean, it replaces multiple symbols, it handles freeform curves effortlessly, and you can customize it with datums and modifiers to do exactly what you need. But this brings us to a really fascinating question. How do you handle these extreme form and location tolerances on a part that isn't static? What if the part is rapidly spinning on an axis, like a drive shaft or a brake rotor? Well, that requires a completely different approach, and we are going to unpack all of that in Lesson 8 when we explore run-out tolerances. Until then, take a look at your next drawing and ask yourself, could a single profile tolerance replace all this clutter? I'll see you in the next explainer.
Lesson 8. Runout tolerances, circular, and total runout. Let's dive right in.
Welcome back to the GD&T Masterclass. Listen, picture this scenario. You've got a newly machined shaft right off the lathe. You take out your calipers, you measure the diameter at multiple points, and boom, it is absolutely perfect, dead center of your size tolerance. But then, you assemble it into your motor, turn the power on, and the thing violently wobbles, literally causing the whole machine to vibrate. What on earth went wrong? We have a perfectly sized diameter, but a completely failing part.
So we have a total pattern interrupt here. A standard static measurement, like what you get from a caliper, only tells you local size. It actually tells you nothing about how that surface behaves relative to its center of rotation. But when we introduce our primary tool for visualizing rotational error, the dial indicator, everything changes. When you place a dial indicator against a rotating part, that needle swinging back and forth is revealing hidden errors that a static caliper will leave you completely blind to. The size is perfect, sure, but what is that swinging needle actually measuring? Well, it's measuring runout.
Let's look at the official rulebook. According to the ASME Y14.5 standard, section 3.55, runout is a general term applying to both circular and total runout, controlling surfaces of revolution relative to a datum axis. The absolutely crucial point here is that runout is always, and I mean always, a rotational, datum-based control. You simply cannot have a runout tolerance without a datum axis to rotate around. It's fundamentally tying the surface of your part back to the exact axis it's going to spin on in real life.
To really wrap our heads around this, let's break down the physical inspection reality into 3 mandatory steps. Step 1, you establish the datum axis. This usually means chucking the part up or resting it in V-blocks on its datum features. Step 2, you rotate the part 360 degrees around that established axis. And step 3, you measure the variation using your dial indicator. Every single runout check in the world relies on this exact physical rotational relationship. So let's look at our first specific type and see how this actually works. This is circular runout, defined in section 3.55.1. Notice the phrase here, each circular element. Circular runout looks at a single 2D cross-section at a time as the part rotates. Imagine slicing your part like a loaf of bread. Circular runout really only cares about the crust on one single slice at a time. The dial indicator stays perfectly still in one spot while the part completes its 360-degree rotation. Digging into the characteristics, the tolerance zone for circular runout is bounded by 2 coaxial circles. Because it's evaluated at independent cross-sections, it effectively catches both circularity, which is how round the part is, and coaxiality, meaning how far off center it is. But remember, it only catches these combined errors at that specific 2D slice. If you move the indicator an inch down the shaft, you are starting a completely new, totally independent circular runout check. Okay, now let's contrast that with total runout, which you'll find in section 3.552. Notice the subtle but massive change in the text here. It's the condition where all elements of a surface are at zero variation, not each circular element, but all of them. We're shifting from a 2D slice to a full 3D surface. Total runout applies to the entire cylindrical surface simultaneously.
Because of that, the tolerance zone totally changes. Instead of two coaxial circles, total runout is bounded by two coaxial cylinders. It literally forces every single cross-section of that shaft to live within the exact same two cylinders. This not only restricts the rotational wobble at any given point, but it also restricts how much the surface can taper or curve across its full length. It is a much stricter and much more comprehensive control.
Comparing these directly, you can really see the jump in complexity. Circular runout is 2D, total runout is 3D. Circular uses two circles as its zone. Total uses two cylinders. And looking at what they actually control, circular controls form and coaxiality for just that one slice. But total runout adds straightness and profile to the mix because, again, it sweeps across the entire surface.
All right, quick quiz time, just to make sure we're tracking. Let's say you have a machinist inspecting a shaft. Setup A has a stationary dial indicator touching one point on the spinning shaft. Setup B has the indicator sweeping continuously across the entire length of the spinning shaft. Which physical setup corresponds to which GD&T symbol? Take a second and mentally map the inspection setups to what we just went over.
Okay, if you guessed that the stationary setup is circular runout and the sweeping setup is total runout, you nailed it. That physical difference inspecting a 2D slice versus sweeping a 3D surface is exactly how you need to visualize these two symbols on your drawings. Sweeping the indicator guarantees that every single point on the surface falls within those two perfect imaginary coaxial cylinders.
Now, I want to let you in on a little secret. Total runout is often misunderstood, but it is actually a 4-in-1 tolerance superpower. When you drop a total runout symbol onto a drawing, you are secretly doing the heavy lifting of 4 completely different error controls simultaneously. Let's break down exactly what errors this single symbol is hunting down for you. According to section 12.4.2 of the ASME standard, total runout provides cumulative control of 4 variations. First, circularity. Is the part perfectly round? Second, cylindricity. Is it a perfect cylinder? Third, straightness. Does it taper or bow across its length? And fourth, coaxiality. Is the center of the part perfectly aligned with our datum axis? By sweeping that indicator, total runout catches all 4 of these errors combined. If that needle stays in the green, you instantly know all 4 of these conditions are good to go.
So why does all this matter? What's the real business value here? Well, this brilliantly illustrates why experienced engineers absolutely love runout. If you use position or concentricity to control a rotating shaft, a machinist usually has to take the part entirely off the machine, bring it to a climate-controlled room, and set it up on a highly complex coordinate measuring machine, or CMM. But with runout, they can literally just slap a magnetic base and a dial indicator right onto the lathe, spin the part, and verify it in seconds. It is drastically cheaper and just so much easier for manufacturing.
Let's move to another really fascinating point detailed in Appendix A14.5 of the standard, and that's the independence of size and runout. You can actually give a machinist a beautifully large, loose tolerance on the diameter size itself while simultaneously applying a super tight runout tolerance. This means you're basically telling the shop, hey, I don't care exactly how thick this shaft is as long as it's within this wide range, but whatever size it ends up being, it absolutely cannot wobble when it spins. This saves you money by opening up size tolerances while keeping the functional rotational requirement strictly controlled.
Now, we've talked a lot about saving money today with simple dial indicators and wide size tolerances. But I gotta tell you, there is a massive concept lurking in the GD&T rulebook that most engineers completely ignore, and they leave countless manufacturing dollars on the table because of it. It's a little something called bonus tolerance.
And that is exactly what we are going to unpack in our next explainer. We're going to dive deep into maximum material condition and show you exactly how to unlock that hidden bonus tolerance. So, ask yourself right now, how much manufacturing money are you currently leaving on the table just because you aren't using it? Join me in Lesson 9 and let's find out.
Welcome to this explainer. Today, we are covering Lesson 9, Material Condition Modifiers and Bonus Tolerance. And right off the bat, we are going to look into a claim that, honestly, to anyone who's ever worked on a shop floor, sounds absolutely impossible. we're going to see how a manufactured part's position tolerance can legally grow bigger, meaning you get way more room for error as the physical feature itself is manufactured smaller, or vice versa. And just to be super clear here, no, that's not a typo on the drawing, and nope, it's not a mistake by the inspector. It's actually specifically designed that way in the ASME Y14.5 standard. So let's unlock the secrets of material condition modifiers together and find out exactly how to get your hands on that completely free bonus tolerance. Okay, so let's just dive right into this paradox. I want you to picture a standard clearance hole drilled into a metal plate and imagine it's shrunk down to its absolute smallest allowable size. Right at that specific, tiny size, the positional tolerance, that imaginary cylinder where the center axis of the hole has to perfectly sit, is incredibly strict. But now imagine your machinist drills that exact same hole just a tiny bit larger. As that physical hole grows, the positional tolerance zone actually expands right along with it. You literally get free tolerance. But why? Why does making a hole bigger make its position requirement more forgiving? Well, it all comes down to function. Think about it. If your only goal is to pass a bolt through a hole, a larger hole naturally gives that bolt way more wiggle room, right? The GD&T standard brilliantly captures this physical, real-world reality and translates it directly into mathematical leniency. To really understand where this free tolerance comes from, we first have to look at the absolute worst-case formating condition. This is formally defined in ASME Y14.5, section 3.41, and it's known as maximum material condition, or MMC. You've probably seen this before. It's represented on blueprints as a little m inside a circle, right there in the feature control frame. So what is it? Well, MMC is exactly what it sounds like. It's the state where a feature contains the absolute maximum amount of physical material while still staying within its stated size limits. So if you're making a hole, MMC is the smallest allowable hole diameter. Why? Because leaving the hole small means you're leaving more metal on the part itself. On the flip side, if you have a shaft or a pin, MMC is the largest allowable diameter. Basically, MMC represents the heaviest possible part you can make. And functionally speaking, this is the worst-case scenario for two parts actually fitting together. A minimum hole trying to accept a maximum pin, that is going to be your tightest, most difficult fit, for sure. Now, we also have the exact opposite extreme, which is known as a least material condition, or LMC. You're going to see this one on a drawing as an L inside a circle. As defined in section 3.40 of the standard, LMC is the condition where a feature contains the least amount of material within its size limits. So for a hole, this would be the absolute maximum allowable diameter. Or for a shaft, the absolute minimum allowable diameter. This is basically the lightest possible part you could produce. Now, while MMC is usually all about making sure parts can successfully assemble together, LMC serves a completely different, but honestly equally vital purpose. LMC is primarily used to protect critical part features. For example, let's say you have a hole positioned super close to the edge of a part. You'd use LMC to guarantee a minimum wall thickness or a safe edge distance. It basically ensures that even at its largest size and worst possible position, that hole isn't going to just break right out through the side of your part. So contrasting these two extremes, you've got the heaviest part on one side and the lightest part on the other, actually reveals the secret to everything we're looking at today. You see, bonus tolerance only comes into play as a manufactured feature departs from its maximum material condition. When an engineer slaps an MMC modifier in the feature control frame, they are locking the stated positional tolerance exclusively to that extreme MMC size. So if the machinist makes the part at that exact worst-case size, they get exactly the tolerance stated on the drawing, not a single micrometer more. But, and here's the real game changer, if the feature departs from that worst-case size, like if they drill the hole just a bit larger, moving away from MMC and towards LMC, the standard literally grants you that exact difference as extra free bonus tolerance. But wait a second, what if you look at your drawing and there's no M or L modifier in the feature control frame at all? It's just blank. Well, since the 1994 revision of the ASME Y14.5 standard, there's been a very strict default rule for this. If you do not specify MMC or LMC, the standard automatically defaults to RFS, which stands for regardless of feature size. And what this means is that your geometric tolerance is strictly, rigidly fixed, completely regardless of the produced size of the feature. It absolutely doesn't matter if you drill the hole at the MMC limit, the LMC limit, or anywhere in between, your positional tolerance stays exactly the same. Under RFS, you get absolutely zero bonus tolerance. Now, RFS is totally crucial for things like rotating shafts where perfect balance and alignment are critical. But from a manufacturing perspective, it's way harder and a lot more expensive to produce, simply because you don't get any of that extra mathematical forgiveness. Okay, let's look at how this builds into a running numeric example, just to prove exactly how departure from MMC size directly equals bonus tolerance. The math here is beautifully simple. It is literally a 1-to-1 ratio. To find your bonus tolerance, you just take the actual produced size of your feature, whatever you measured right there on the shop floor, and you find the absolute difference between that and the MMC size specified by your limits. That difference, that is your bonus tolerance. Then to find the total available tolerance for your part, you simply take the original stated tolerance from the feature control frame and add your newly calculated bonus tolerance right to it. This new combined number is the true functional tolerance zone your part's axis is legally allowed to drift within.
All right, before we move on to the next major concept, I want to do a quick pop quiz. Let's see if we can calculate the total available position tolerance together based on these three numbers. Imagine you're out there inspecting a part. Step 1, you check the blueprint and it says the minimum hole size, which is the MMC, is 14.0 millimeters. Step 2, you measure the actual physical hole the machinist produced and it turns out slightly larger, let's say 14.2 millimeters. Step 3, you look back at the feature control frame and the stated positional tolerance is 0.5 millimeters with an MMC modifier. Take just a second to think about it. What is your total true positional tolerance for this specific hole? Got it in your head? The answer is 0.7 millimeters. This brilliantly illustrates the math we just talked about. We take our produced size of 14.2 millimeters, subtract the MMC size of 14.0 millimeters, and that gives us a difference of 0.2 millimeters. Boom, that is our free bonus tolerance. We then take that 0.2 and add it directly to our stated 0.5 millimeter tolerance from the blueprint, giving us 0.7 millimeters total. By simply drilling the hole slightly larger than the absolute minimum, the manufacturer just gained a massive 40% increase in their positional tolerance. Honestly, that is often the difference between throwing a really expensive part straight into the scrap bin and legally passing it for functional assembly. This right here is exactly why manufacturers absolutely love the MMC modifier. So, the crucial point that ties this whole shebang together is understanding virtual condition, or VC. ASME Y14.5 section 3.7 defines this as the absolute worst-case boundary that a feature can generate. Basically, it is a constant, completely unmoving boundary generated by the collective effects of a feature's MMC or LMMC size along with its geometric tolerance. I like to think of it as an invisible 3D envelope floating in space. Imagine you have a hole at its absolute smallest size, and then that hole's position shifts all the way to the extreme edge of its positional tolerance zone. The resulting theoretical 3E shape left over in that space, that is the virtual condition. It is the absolute functional limit of assembly. The standard actually provides two different ways to interpret this, but the primary one, and definitely the most important one, is called the surface method. Section 5.9.4.1 explains that when a geometric tolerance is applied on an MMC basis, the feature's physical surface shall not violate the virtual condition boundary. Practically speaking, this means you don't even need to calculate the exact invisible axis of the hole to know if the part is good. As long as the physical limits of the manufactured surface do not cross into this constant virtual boundary envelope, and assuming the part is still within its general size limits, your part perfectly passes inspection. It will assemble, it will function. Period. And guys, this is the exact reason physical go/no-go gauges work perfectly on the shop floor. A functional gauge is quite literally just a physical manifestation of that virtual condition boundary we just talked about. For example, if you calculate the virtual condition of a hole to be exactly 13.5 millimeters, you can literally just machine a hard steel gauge pin to exactly 13.5 millimeters, set it perfectly at true position, and you're good to go. If that pin drops into the manufactured hole, the part passes. Why? Because the surface didn't violate the boundary. This also completely explains why parts toleranced at RFS, regardless of feature size, cannot be checked using these same fixed gauges, because RFS doesn't give you any bonus tolerance. Its boundary isn't constant. It shrinks and grows depending on the produced size of the feature, meaning a single fixed size physical gauge pin just won't work. Now, everything we've discussed today assumes perfectly rigid, standard parts where we can reliably measure from nice, flat surfaces. But consider this for a second. What happens when your part is, say, a super rough casting, or a warped, flexible piece of sheet metal, or even something massive like an entire aircraft wing? Without flat surfaces, all these beautiful, precise tolerance calculations suddenly lose their anchor. So how do you measure the unmeasurable? Well, keep that question in mind, because in Lesson 10, we are going to explore datum targets and advanced datum concepts to solve that exact problem. Until then, keep analyzing those prints and always look for that free bonus tolerance.
Welcome back to Lesson 10 of our GD&T Masterclass Explainer. Up until now, we've been dealing with pretty straightforward, rigid parts. But today, Today, we're tackling a massive, real-world manufacturing headache. We're diving into advanced datum concepts and datum targets, straight out of the ASME Y14.5 standard. Imagine you're handed a huge, flexible sheet metal panel, or maybe a rough casting fresh from the foundry. If you try to place that warped, highly imperfect part on a perfectly flat inspection plate, well, it's going to wobble. It's going to rock back and forth like a bad table at a restaurant. So how on earth do you establish a reliable datum on a surface that is literally never perfectly flat to begin with? Okay, let's dive into this, because the technique we're about to cover is the exact solution used every single day across aerospace and automotive to solve this precise nightmare.
Picture a failed measurement attempt for a second. You try using a full-surface datum on a flat granite table. Because the part is warped, the contact is completely inconsistent. One inspector presses down on the left side, the next inspector presses down on the right, and boom, they get totally different measurements. Now picture replacing that flat table with 3 specific target points, fixture pins acting as datum feature simulators. Which of these setups do you think is going to give you the exact same measurement every single time, no matter who's holding the calipers?
Section 1. Mastering datum targets. Let's see exactly how we manage these imperfect physical parts using the core rules.
So looking at paragraph 321 of the standard, it defines a datum target as the designated points, lines, or areas that are used in establishing a datum. You got to remember our core concepts here. A datum is a perfect theoretical concept. It doesn't actually exist in the physical world. The part itself is always imperfect. So to bridge that gap on warped or rough parts, we use physical datum feature simulators, think rounded tooling pins or specific chucks, to make actual contact with the part at precise, clearly defined target locations.
And this brilliantly illustrates the clash between engineering theory and shop floor reality. Paragraph 7.24 explicitly tells us we just can't use an entire surface to establish a datum when we're dealing with inherent irregularities. We absolutely need datum targets when we're working with rough castings, forgings, or molded parts. We need them for complex weldments, and we especially need them for thin section surfaces like sheet metal or plastics that are prone to bowing, warping, or just generally distorting.
All right. Let's test your engineering intuition for a second. If you've got a wobbly, flexible sheet metal panel, how many individual target points do you think are needed, at a bare minimum, to establish a stable, primary datum plane? Go ahead, take a guess.
The answer is 3. Yep, paragraph 7.24.4 dictates that a primary datum plane is established by at least 3 target points that are not on a straight line. It's just like a 3-legged stool. It literally never wobbles, even on a terribly uneven floor. Building on that, a secondary datum plane usually requires 2 targets, and a tertiary requires 1. This 3-2-1 principle is the absolute rock-solid foundation of fixturing.
Section 2. Reading datum target symbols. We know why we need them, so let's look at how we actually document them on a drawing. Now, what's really interesting about this symbol is its unique visual anatomy. It's a circle divided horizontally right in half. The lower half contains the letter of the datum it helps establish, followed by a sequential number. So for example, A1, A2, and A3 would be the 3 targets creating primary datum A. And notice how a radial line connects the symbol directly to the exact target location on the part drawing. In a 3D model, this leader line is always solid, pointing exactly to where the physical tooling pin needs to touch.
According to section 6.33, that radial line can point to 3 distinct types of targets. First up, a target point, indicated by a simple X symbol. Second, a target line, shown as a phantom line on a direct view or a point on an edge view, which is super common for cylindrical parts. And third, a target area, indicated by section lines inside a phantom outline. You'd use the target area when your tooling pin needs a flat, defined contact patch rather than a single sharp point, and its basic dimension of size and shape will always be explicitly specified.
Okay, let's pause for a quick reality check. So the crucial point is this. Datum targets are located using basic dimensions. They represent exact, theoretical coordinates. If the manufacturing engineer designs a physical holding fixture, and the quality inspector programs their coordinate measuring machine, their CMM, but they don't use the exact same target locations, oh man, you have a disaster on your hands. Your fixture won't match your CMM program, and you'll end up scrapping perfectly good parts simply because the part was held in one location during machining and probed in a totally different location during inspection. Alignment is literally everything here.
Section 3. Simultaneous requirements and restraint. Now that our parts are secured, let's look at how multiple geometric controls interact.
The standard introduces this really fascinating concept in paragraph 3.56 called a simultaneous requirement. Basically, this is a condition where two or more geometric tolerances apply together as a single pattern. If you have multiple position or profile tolerances and they're located by basic dimensions relative to the exact same datum features, referenced in the exact same order of precedence, and at the same material boundaries, well, they act as a single locked requirement. There's absolutely zero translation or rotation allowed between their datum reference frames. They're inspected together simultaneously as a single unit.
But what if the part's physical function doesn't actually require those distinct patterns to be locked perfectly together? If that interrelationship just isn't necessary, the designer must explicitly break the simultaneous requirement by placing the notation sep-rect, which simply stands for separate requirement, right next to each applicable feature control frame. This is a game changer because it frees up the inspector to optimize the setup for each pattern independently, potentially saving parts that are totally functional but might have failed a strict simultaneous inspection.
Section 4. Customize datum reference frames. Let's do a quick preview for when standard rules just don't cut it. Let's see how this builds our understanding when we look at standard versus customized frames. Normally, when we reference primary, secondary, and tertiary datums, the standard applies a default set of rules for how degrees of freedom, like translation and rotation, are constrained. But paragraph 722 outlines customized datum reference frames. When a high-level expert is dealing with some bizarrely shaped part where the physical function demands it, they can explicitly override those default constraints. They can declare exactly which degrees of freedom each datum feature is allowed to lock down, customizing the restraint specifically to how that crazy part functions in the real world.
And that brings us to our next segment, real-world print reading. We've covered an immense amount of ground today.
You've just leveled up. Dealing with warped parts, target symbols, simultaneous requirements, customized restraints, you now have the theoretical toolkit of an advanced GD&T practitioner. But theory is absolutely nothing without execution. So in our next explainer, Lesson 11, we're going to put every single rule, symbol, modifier, and theory we've learned so far to the ultimate test. We'll be walking through a complex, real-world production print from top to bottom. Before we go, ask yourself this. If a single misaligned datum target can ruin a $1,000 casting, how confident are you in reading a fully loaded feature control frame? Think about it, and I will see you in the next explainer.
All right, let's jump right into Lesson 11. We've spent our previous sessions really digging deep into the intricacies of ASME Y14.5 and poring over all those GD&T reference sheets. We've covered the theory, the symbols, the rules, you know the drill. But today we're putting it all together. We are taking all of that theoretical knowledge and slamming it right into a real-world scenario. This is exactly where the rubber meets the road, guys. It's where we take individual abstract concepts and turn them into a total, comprehensive understanding of engineering product definition. And I'm going to make a pretty bold promise to you right out of the gate. By the time we finish this explainer, you are going to read a massive, fully toleranced production drawing like it's your native language. No joke. We're not going to just hunt and peck around the page trying to translate it symbol by agonizing symbol. We're going to read it as one cohesive, logical story. Because, well, when you truly get GD&T, a drawing isn't just some boring list of instructions. It's a literal narrative about how a part actually functions in the real world, how it interacts with other components, and exactly which constraints are absolutely crucial. Now, when you first glance at a real-world high-density production drawing like this one, yeah, it is intentionally overwhelming. Your eyes are probably darting all over the place. You're seeing boxes, circles, letters stacked on top of each other. It looks like absolute chaos. It's like a giant puzzle dumped on a table. But hey, don't panic. The secret to cutting through all that noise lies right in the core rules of the datum reference frame and those feature control frames. Once we ground ourselves in those basics, the whole thing just clicks. So let's cut through that chaos right now. We're going to zoom straight into the ultimate anchor of any drawing, the datum reference frame. Specifically, datum features A, B, and C. Everything, and I mean literally every single geometric tolerance on a print, every intricate little control branches directly from these three letters. They are the absolute foundation. Now, remember, according to the ASME Y14.5 standard, datums are theoretically exact points, axes, or planes derived from the true geometric counterparts of our specified datum features. So they're perfect in theory, and they are exactly what ties this messy, physical, real-world part back to the pure mathematical design intent. Okay, so how do these datums actually work together to anchor our part? Let's walk through it step by step. Picture a rigid body just floating in 3D space.
It has 6 degrees of freedom, or DOF. That's 3 translational, moving along the X, Y, and Z axis, and 3 rotational, spinning around those exact same axes. So step 1 is our primary datum. This physical feature actually contacts our datum simulator at a minimum of 3 points. Boom, that establishes our first plane and locks down 3 degrees of freedom, usually 2 rotations and 1 translation. Then we hit step 2, the secondary datum. This one contacts at a minimum of 2 points, perfectly perpendicular to the primary, locking down 2 more degrees of freedom. And finally, step 3, the tertiary datum. This feature just needs to touch at a minimum of 1 single point, perfectly perpendicular to both the primary and secondary datums. That strips away the very last single floating degree of freedom. Once A, B, and C are established in that exact order of precedence, the part is completely and fully constrained.
Right, so with our part firmly anchored, we can finally start reading the feature control frames, the FCFs, that tell us our exact tolerances. And you always read a feature control frame from left to right. First up, you've got the geometric characteristic symbol. This represents one of the 14 core categories, like position, flatness, or perpendicularity. Next comes the tolerance value itself. And remember, this might have a little diameter symbol in front of it if the tolerance zone is a cylinder. Third is the material condition modifier, assuming one actually applies. And finally, the datum references in their specific order of precedence, primary, secondary, and tertiary, and each of those might even have its own modifier. But honestly, you just read it left to right, exactly like reading a sentence in a book. Okay, hold up. Before we go any further, let's pause for a really quick pop quiz. Take a look at the specific feature control frame right here. You see that little M inside a circle right after the tolerance value? What does that M symbol dictate in this context? Think back to our earlier lessons. I'll give you a second. Actually, drop your guess in the comments right now before I give away the answer. Did you nail it? That M stands for Maximum Material Condition, or MMC. Basically, this modifier dictates that the stated tolerance only applies when the feature contains the absolute maximum amount of material allowed. Think, the smallest possible hole or the largest possible pin. But here's the real magic of MMC and why it's an absolute game changer in manufacturing. As the physical feature departs from its maximum material limit, like say that hole gets drilled just a tiny bit larger than its minimum size, you actually get bonus tolerance. We covered this back in lesson 9, but seeing it applied here shows exactly how a machinist gives extra wiggle room for location or orientation, all while guaranteeing the part will still perfectly clear its mating component. It lowers manufacturing costs and ensures everything still fits together. It's brilliant. Now, I want you to keep your eyes sharp because there is one feature control frame on this drawing that looks incredibly simple at first glance. It doesn't have a bunch of crazy modifiers or a super long list of datum callouts, but secretly, it's acting as a master constraint, controlling 3 completely different geometric characteristics simultaneously. Scan the print really quick. See if you can catch which one it is before I spill the beans. If you guess the profile tolerance, you hit the nail right on the head. Under ASME Y14.5 rules, a profile tolerance zone is ridiculously versatile. Depending on how it references the datum reference frame, a single profile callout can control the form of a feature, its orientation, and its location, all at the exact same time. It basically creates this uniform boundary, like a perfectly fitted envelope all the way around the true, theoretically exact profile of the part. And if that callout includes primary, secondary, and tertiary datums, well, that tolerance zone is fully constrained in both translation and rotation. So a machinist doesn't need separate confusing callouts for flatness, perpendicularity, and position. Profile just handles the whole shebang in one elegant, though highly strict command. Now, as you read through the rest of the print, you kind of have to start categorizing the story it's telling you. Because let's be real, not all tolerances hold the same weight on the shop floor. We generally split them into 2 buckets: functional tolerances versus cosmetic or non-critical tolerances. Functional tolerances are your assembly and fit critical controls. Think of position and orientation tolerances that reference back to your datums. These are the big ones. They guarantee that a bolt will actually slide through a clearance hole, or that a bracket will sit totally flush against its meeting assembly. On the flip side, you have cosmetic or independent form controls. Think of a loose flatness or straightness callout that doesn't even reference a datum. Distinguishing between these 2 is absolutely crucial. Why? Because it dictates your manufacturing and inspection priorities. You spend your time, your money, and your high-precision machining on the functional, fit-critical features, and you let the cosmetic ones run a little faster and cheaper. And that brings us right back to how we approach any project. Because you understand these governing rules now, this print is no longer just a chaotic web of meaningless lines and symbols. Look at it! It's one cohesive story. You know exactly how datums A, B, and C anchor the part in space. You know how to fluidly read feature control frames from left to right. You can spot those MMC modifiers that save tons of manufacturing cash. And you recognize the sheer power of a profile tolerance. You, my friend, can now fluently read the language of engineering intent.
But here's the kicker. Understanding the language of the print is really only half the battle. Sure, we know what the part is supposed to look like in a perfect world, and we know exactly how much it's allowed to deviate from that perfection. But how do we actually prove it? How does a quality inspector take a physical, imperfect piece of metal, lock it into a physical datum feature simulator, and actually verify that it meets every single one of those strict criteria we just decoded? And what happens when a whole bunch of parts with all these different tolerances stack up together in an assembly? Will they still fit? Well, that is exactly what we are going to tackle in Lesson 12, Inspection and Tolerance Stack-Up Basics. You won't want to miss it. Stay tuned.
Welcome to the finale of our GD&T Explainer series. We're tackling Lesson 12 today, Inspection and Tolerance Stack-Up Basics. We've covered a ton of ground so far, but today we are finally solving the ultimate manufacturing mystery that literally every engineer faces at some point. So here's the paradox. Every single individual part passes inspection, right? So why doesn't the assembly fit? Imagine you've got 3 pristine parts. Green check marks across the board. They're verified 100% within tolerance. But you go to assemble them and boom, there's a massive gap. Or maybe they just completely clash. If absolutely nothing failed inspection, where on earth did this invisible error come from? Chapter 1, the verification disconnect. Let's figure out where this error is hiding by looking at how these parts are actually verified on the shop floor. You see, the way a part is measured dictates how it behaves in an assembly. We typically use a few primary methods. Sometimes we use a CMM, a coordinate measuring machine, to mathematically derive the axes and surfaces. Other times we rely on functional or fixed gauging, using physical datum feature simulators, like a gauge pin or a chuck. The thing is, the measurement method you choose fundamentally changes how a feature control frame is interpreted. And this brings us to a huge point in the ASME Y14.5 standard. Depending on whether you use the surface method or the axis method, the allowable geometric variation behaves completely differently. With the surface method, your feature's surface absolutely cannot violate the virtual condition boundary. That means you literally get 0 geometric tolerance if the part is produced at its maximum material condition limit of size. But with the axis method, the tolerance zone actually gets bigger as the feature size departs from MMC. So, if you aren't accounting for how the part is verified, your assembly is already walking into a trap. Moving on to Chapter 2, the stack-up reality. Once you know how individual parts are measured, you have to deal with how those individually acceptable variations pile up. You generally have 2 ways to calculate this. First is worst-case tolerancing. This is where you just assume the absolute extremes and add the maximum variations directly together. Then you have statistical tolerancing. This uses sound statistics, like a root-sum-square formula, to loosen individual limits. Doing this can save you a ton of money in manufacturing while still shipping a working product. But there's a major trade-off that nobody tells you about. And that catch is right here in the ASME standard. If you rely on the forgiving math of a statistical stack-up, you are strictly mandated to manufacture using statistical process controls. You can't just slap a statistical symbol on a blueprint to get looser tolerances and then run your machines like normal. If your process isn't statistically controlled, you have to default back to those more restrictive, worst-case arithmetic limits. Chapter 3, Precedents and Boundaries. Let's look at how material conditions alter our math. Going beyond basic verification, we have to realize datum precedence directly alters our stack-up limits. Just look at how this builds when calculating a worst-case material boundary for an external feature of size. For the primary datum, the outer boundary is just your maximum material condition plus the straightness tolerance. Simple enough. But check out the secondary datum. Now you're taking MMC plus perpendicularity plus straightness. And by the tertiary datum, you're combining MMC, position tolerance, and straightness to form this massive outer boundary. These tolerances literally stack up on top of each other before you even try to mate 2 separate parts together. All right, Chapter 4, the final calculation. Let's combine these feature control frames into a real assembly gap calculation. Now it's your turn to get in the driver's seat. Take a look at this setup. We have what the standard calls a fixed fastener case, like a screw in a tapped hole. We've got a fastener diameter, F, and positional tolerances for the two parts, T1 and T2. We need to figure out H, the required clearance hole size. Before we reveal the standards formula, actually just take a second to mentally calculate it. What's your estimate for the worst-case stack-up hole calculation to guarantee a fit? Got a number in your head?
Here's the reveal. The absolute limit for the fixed fastener clearance hole is the fastener diameter plus the positional tolerance of the first part plus the positional tolerance of the second part. H equals F plus T1 plus T2. If you don't provide this combined clearance, a threaded hole that is perfectly in tolerance on its own might be just out of square enough to completely crash the assembly. So how do we actually apply this? Step 1, you identify your dimensions, feature control frames, and fastener type. But pay close attention to step 2. You absolutely must check if you're using chain dimensioning or baseline dimensioning. The standard warns that chain dimensioning causes the greatest tolerance accumulation, a total nightmare for stack-ups, whereas baseline dimensioning reduces it. By following these exact steps and calculating our H equals F plus T1 plus T2 formula, that 3-part assembly from our very first slide is now correctly toleranced. That glowing red gap is totally gone and everything fits perfectly. And that brings us to Chapter 5, the complete picture. This mathematical proof right here, it's the final piece of the GD&T puzzle. It bridges the gap between a single inspected part and a functional final product. All the way back in Lesson 1 of this explainer series, we talked about the disastrous costs of ambiguous tolerancing, scrapped parts, failing assemblies, massive arguments between engineering and the shop floor. But now, you hold the complete system to prevent all of that waste. To really lock this in, I highly encourage you to go back and re-watch specific explainers in this masterclass to reinforce these concepts. As you apply this to your own drawings, it's an absolute game changer. Be sure to subscribe and let us know in the comments, what specific GD&T topic or obscure ASME rules should we dive into next? Until then, I'll leave you with this. Are the tolerances on your blueprint stacking up to reality, or are they just hiding invisible errors waiting to happen? Keep questioning your designs. Video title Tolerance Stack-Ups Explained, Why Past Parts Fail. 3 thumbnail concepts. 1. The gap. A split screen. Left side, a green checkmark over a single pristine part, passed. Right side, 3 of those parts assembled, but there is a massive glowing red gap between them. Failed. 2. The equation. A close-up of a blueprint with 2 simple FCFs pointing to a giant red question mark where the parts mate. Bold text overlay, worst case versus statistical. 3. The clash. 2 physical parts crashing into each other, interference fit, with sparks or a red highlight at the crash point. Text overlay, but the CMM said it was perfect. 1-line YouTube description. Every individual part passed inspection, so why doesn't the assembly fit? Here's the final piece of the GD&T puzzle, tolerance stack-ups.